So I'm Sally Kleinfeld. This is Matthew Wilkes, Alec Mitchell, and David Glick. You probably know them all anyway. And we're going to talk about a really interesting project that we're doing right now. All right. So first I'm going to talk about the program. Next slide. This program is called the Next Generation Social Sciences, also known as NGS2. It's a big program funded by DARPA, which stands for, closer? Okay, thanks. Thanks for the reminder. Which stands for the Defense Advanced Research Projects Agency. It is, in fact, an agency of the US Department of Defense. It was originally ARPA, which was created in response to Sputnik back in 1958. Ooh, we have to develop technologies and stay leading edge. And it was the agency that created the ARPANET, the precursor to the internet, the first network to implement TCP/IP. So DARPA/ARPA has had a long history of developing leading edge technologies in the United States and really worldwide. So I offer you a quote about the basic aim of the NGS2 program. Basically, the desire is to scale up social science modeling and the experimental methodologies that are available so that you can potentially include thousands of people in experiments instead of the typically very small sample sizes that social scientists are often dealing with. The goal is to identify the primary drivers of social cooperation, social instability, social resilience. So to study what unifies individuals and what causes communities to break down, AKA also known as probing the sources of social unrest, thus the interest that DARPA has in it. So there are certainly benefits for this kind of scaling up these kinds of experiments in all sorts of fields, public health, economics, but also national security. It certainly is a useful thing to be able to more clearly understand terrorist communities and et cetera. All right, so the initial focus of this program, they decided that they should do a sample, narrow in on one particular problem area. It's rather a large area, and that is to identify causal mechanisms of collective identity formation. So what drives the emergence or collapse of collective identities in humans? What unifies individuals? What causes communities to break down? And this was to be used as just an example that can be used to sort of take off with studying other complex problems like resilience in social networks or changes in cultural norms, all sorts of interesting problems that people like to study. Next slide. So, so now I'll talk a bit about Dallinger, specifically the system we're working on. Next slide. So one of these cooperative agreements, it was a big competition for soliciting work on this problem area. And a team led by the University of California Berkeley's Computational Cognitive Science Laboratory was one of 4 teams that were awarded cooperative agreements for the NGS2 program. So it's a very large grant, $5 million or something big. I don't even remember. So we are developing, the team is developing Dallinger, which is a software platform for laboratory automation in the social sciences and behavioral sciences. So a little bit more about Dallinger. It's a platform for crowdsourcing experiments. The idea is to be able to abstract the experiment into a single function call that can be inserted into higher order algorithms, like you might want to progressively refine your experiment. The experiment itself is captured in software, and you want to be able to refine the experiment based on the results. So these kinds of algorithms, this is the goal. We're not there yet, but this is the long-term goal of Dallinger. And in order to do that sort of thing, the whole process of doing the experiment is automated. So the system recruits participants, in our case right now, on Mechanical Turk, although the idea is to be able to have other recruitment platforms in the future, obtains their informed consent, arranges the participants into a network, runs the experiment. The Heroku is where the actual, it's a web application essentially that the experiment is, sort of. Please, you guys, interrupt me when I say something that's wrong.
You haven't yet.
So run the experiment, coordinate the communication among all these users, record the data that's produced, pay the participants, because on Mechanical Turk, you sign up to do hourly work or minute-by-minute work, and you're paid by the time that you spend, so it pays the participants automatically, recruits new batches of participants, contingent on the structure of the experiment, and validates and manages the resulting data. So it does a lot. How does it work? Basically, and we can, I'm talking really fast, and I apologize for doing so, but I wanted to just push through a very high-level explanation, and these are all things that you can ask questions. We're going to try to leave a lot of time for questions and discussions. So the experiments themselves are modeled as directed graphs. You can sort of think of the experiments as if they were Plone add-ons, not literally the same technology, but the same idea where you have this system and you can add on something else and run it. So the system, Dallinger, runs experiments. The idea is for researchers to create their own experiments. Although Dallinger comes with a set of, 20 or so sample experiments, each of which runs a sort of classic social science. Like the experiments are known by their bibliographic references, like Bartlett 19 whatever it was is one of Bartlett 1932 was one of the experiments. So that's the basic idea. And basically all the teams, the 4 teams or the 5 teams that were funded by DARPA, coalesced on using a public goods game to pursue the research. Public goods as in there are, somebody help me explain this, there's a set of stuff, like food in the game or whatever, and you have some sort of group of people, either in communities or not or whatever, sort of using and generating the public good. Dallinger, however, is the only team. Dallinger, the team at UC Berkeley, entered the competition for this NGS2 program kind of ahead of everyone else because they had already started creating a platform named something different, but they had created a lot of the infrastructure to do this kind of automation before. So they were far enough ahead that they were actually able to develop a real-time multiplayer game to do the experimental work in Dallinger, and that is called Grid Universe.
All right, so I'm in charge of demoing. Sorry, I'm in charge of demoing this thing, so you're going to get to possibly see a live demo. So this is what, if you were running an experiment from Python, this is what the call would look like. And you can run this sort of thing in a loop with different configuration parameters. Oh yeah, let me expand this here. All right, so there. The experiment in this case is called Grid Universe. We're pulling in 3 participants, though that's not actually being used here. There's a text configuration that provides configuration for the experiment, and that sort of defines the public goods game, exactly this is kind of a Pac-Man-esque game where you run around trying to collect little pellets of food, and the public goods aspect is about you can share that food with other players, share your points you gain from that food with other players or with the group of players that you're with. You can change which group you belong to as you play it.
You can plant more food as well, and then sort of you have to wait for it to mature, so you're not going to do it if there's lots of people from another team near you. But,
right. And you also things like when you move it can leave walls behind you, like a kind of snake-like version of the game. So there are a bunch of different variations of the game you can create by setting configuration parameters. This is the configuration we're going to use for the demo. This is like a basic demo run that just says, you know, import the experiment, which is a Python module, run it, take that data, analyze it, print out the results. I'm going to go into a terminal, which hopefully you can see, and run this experiment. I'm going to run it with 2 Chrome driver-based bots that are going to compete against me doing this thing.
So a hit is like Mechanical Turk lingo for when a user accepts a job, essentially.
So here are the instructions for the game. Those are based on the configuration of the game here. So I'm going to say, I'm going to begin this. And here I am in the game competing against a bot. For some reason, only one of these bots showed up. I'm running around. I'm going to change my color because I don't want to be part of his team. I want to be my own team. And then I'm going to yell at him and go back to moving around. Oh, somebody else is about to join. Chrome driver was slow.
They're too late.
Which color are you?
I'm the red one, but now I'm a blue one.
So the reason for having bots in this is so that you can write a sort of a Python function that defines how you think people will behave in your experiment, and then you can run it with these bots. You can compare it to people in the real world and see, what was my idea of how people behave accurate, or do people actually go a different way? Are they more effective than the bots or not?
So the goal of the program, the DARPA program, is to be able to scale up experiments to tens of thousands of users playing the game simultaneously with mixtures of bots and humans, or all bots or all humans.
Right, and some of these experiments are chained together, where you have a group of people participating, and the results of that become the output for the next group of people. So there are all of these different network structures for experiments. At the end, they always ask some quiz about the experiment. This is the most basic one, but there are some specific sort of graphical questions they ask about how you feel about your group that you were part of during this experiment. I'm going to finish this up, and then I can go back to my terminal here, and we'll
Yeah, the survey is one of the fundamental deliverables for the program. There has to be a survey. There has to be a measure of, what's it called, the Diffie, there's some fancy academic lingo for the measure of the group's cohesion, and another thing.
So during that experiment, every action that was taken by the players, me and the bots, was recorded in a Postgres database as JSON-B data. I can export everything that happened into a zip file, and then I can, if I want to, replay that experiment with a simple command line command. So there's this Dallinger command line that the experimenters use to load up experiments, run them, deploy them to Heroku, recruit people. In a second, we'll get a browser window.
Just to interject here, the goal, another goal is to kind of integrate the system with the open source framework, which is a place for scientists and all kinds.
Open science framework.
Open science framework, sorry. Thank you. To upload their experimental code as well as their experimental results, so that their publications are backed up by public data.
And so you notice the replay is doing the same things that Alec was doing before.
Right. So it replays the chats that were made, the color changes, everything about the game is available in the database to be replayed by the experimenter to see exactly what happened during the course of this. Or analyzed. And then because the experiment itself is a function call, this function call, if it weren't mode debug, this function call would actually create servers on Heroku, create an application on Heroku with, some potentially large number of servers, go out to AWS Mechanical Turk, recruit people, run the experiment with potentially hundreds of people, collect the data, analyze the data, and then you could run this in a loop They took the results of that data analysis. There's like a genetic learning algorithm that you can parameterize, look at the output data, change the configuration for the next experiment in code, and then run it again. So potentially you could have this sort of thing run in a loop over the course of a week, recruiting hundreds of participants at a time, doing your experiment over and over and over across multiple groups of people with small tweaks in parameters.
So as an example of why that might be helpful, I mentioned earlier that you can plant food, but in some circumstances you might not want to because people will swoop in and take the food that you've planted. With this, you can tell the evolutionary algorithm, I want you to vary how long it takes for food to mature, and then optimize it so that people try to plant food as much as possible. And it will start picking numbers and find that the function that describes how likely people are to plant food and defend it depending on how long it takes to grow and mature and be available to harvest.
So that gives you the basic idea, the sort of thing that this particular experiment does that Dallinger is using to investigate. So Dallinger's grant covers two things. One is to create this generic experimental framework for doing experiments, but also to invent an experiment that's going to measure these kinds of questions about collective identity formation. So the grid universe game is what's going to be used for that latter thing, for doing those measurements. And there's just a link to the repository where all this stuff lives. So I'm just going to say a few words about what Jazkarta is doing as part of this. So we were awarded a 5-year contract to help build this system. Why us? Because we have expertise in the technologies that are used, and that's like a whole alphabet soup of technologies which are up there. It's obviously not just Python, but a lot of things. Also because we have expertise in project management, classically not something that, universities have people who know all the bits and pieces, but they don't typically run large projects, so we bring that to them. And we also have, one of the big selling points we had was that we have expertise in running and being part of mature open source project, an open source community, namely Plone, because part of a goal of this is to make this not only just simply downloadable, but to create a whole community around Dallinger that can use it and foster the same sort of community that we have, only not as cool, of course. So our process, we did a discovery meeting in the fall. We generated a whole bunch of user stories, estimated them using Planning Poker, and we're in the process of implementing them in a series of iterations. We've been working essentially since November, December, and we will continue on into next year, and then there'll be a pause, and then there'll be phase 2, assuming that they like the results of what they see, et cetera. So. And our team is the people you see here, plus 2 people who are absent. Carlos de la Guardia and Jesse Snyder are also part of the team.
But this is the Jazkarta team. Because it is an open source project, albeit a small one and a new one, there are people at UC Berkeley and other organizations who contribute as well. It's not just us. It's
Absolutely. Yeah. Sorry, I should have made that clear. We're doing work, but the people at Berkeley are working right alongside us at the core software, and then there are other people at Berkeley and at Arizona State University, and I don't know where all else, that are actually writing experiments, getting trained. And also finding bugs, yes. Another interesting part of the project is there's a visualization team as well, like a data visualization team, which so far we've not worked very closely with them, but I'm very excited and interested to see as we go on what kinds of visualizations they'll come up with. Okay, what I'm going to do now is to launch into a number of sort of question areas, and I'm going to stop talking so much and let everyone else talk more. We just thought of a number of sort of topics that you guys might be interested in, and we'll talk a little bit about each of these topics, and then we'll have hopefully a lot of time for your own questions. We have about a half hour left, guys. All right, so we brought a lot of experience with Plone to this project, and we had learned a bunch of lessons. Anybody want to kind of chat about some of these ideas?
Well, yeah, when you use another framework that's not Plone and they've done something really silly and you think, well, I wish someone would learn from the mistakes we made, like the amount of over-engineering in portlets that we we realized after we'd all converted to it that it was a really bad idea. And if someone had asked us, and they said, we're planning to do this, we could have said no, but nobody ever asks an existing open source community. But for this, we had an advantage, so we could just go and say, no, let's just not over-engineer that. A lot of the sort of the plugin architectures that we've got are really basic, and we're just intending to throw them away and rebuild them if we ever need to, because we haven't sort of heavily invested in them. Do you agree with that, David? You look dubious?
Yeah, no, I think so.
Yeah, and that relates to the breaking backwards compatibility as needed also. We're not afraid to do that. And removing references to old ways of doing things, you guys can probably relate to that. Let's see, there's another set of bullets about this. Anybody else want to talk about?
Yeah, just that we sort of have the luxury of starting, it's not quite from scratch because there was this prior system that we were, that they had built that we have been using as a starting point and making changes to. But to a large extent, we're getting to decide how things will be set up, but we're doing that with all of our knowledge of Plone, and it's not the same sort of, it's not a web framework, but there are these parallels, like the fact that, you know, in Plone we build a site that runs on a framework, and in Dallinger you build an experiment that runs in a framework, so there's things that we know about what things to make reusable that has been valuable knowledge.
And then in terms of process, which is what this next slide deals with, it's because this is an open source project and it's being used in a variety of different ways by a variety of scientists, and hopefully even more in the future. You know, having pretty comprehensive test coverage has been important. Having continuous integration processes, well-defined processes for development, for merging features and releases and whatnot has been really important. And then we're still working through that to some extent, exactly how we want to do some of these production release decisions and breaking change decisions. We've certainly applied a lot of knowledge that we have from working on more mature projects to that process.
Oh, go ahead.
It's a bit different from sort of a normal commercial project, because usually on a commercial project you are the only developers and you use your expertise and you get your way. Whereas with this, we're trying to create a community and we're helping out, we're helping build it, but it has to be a community decision. So although there's not that many people at the moment, we're kind of acting like everyone is on the framework team, and like,
Right.
we have long discussions that are the equivalent of the old framework team phone calls, and like, over time the community will get bigger and our role in that will become less.
Right. We're going to move on to the next topic, but before we do, anybody have questions or the comments they want to make on the sort of lessons learned from Plone, open source communities, and in general? Any questions about that?
I miss Joel Burton too.
Yeah, I know. So do we all.
So for anyone who joined the community after Joel stopped being active, which was quite a long time ago now, which is sad, Joel used to do lots of Plone trainings, and he would come to the conferences with long lists of things that people found confusing that we'd never even thought of, like having separate file types for Word and Excel documents, when there's no technical reason to do that, but if you are trying to learn a new system, you think, well, this isn't a file, this is a spreadsheet, I want to upload a spreadsheet. That kind of insight from someone who spends all of their time talking to end users and knowing what they want was really helpful. And that's something we have with Dallinger, because Jordan and the other people who are on more the social sciences side of things are using this as their day job, and we communicate with them a lot, but oh God, I miss it in Plone. Like, if we had someone who was doing full-time Plone training, I think we would be going a lot faster with good user experience.
That's a good point. Yeah. Let's move on to the more tech stack. So the question I'll throw out here for the assembled guys is, what are the biggest similarities and differences between Plone and Dallinger in terms of the tech stack?
I mean, it's got a component of it that is serving web pages. There's a Flask app that gets deployed to Heroku when you're running the real experiment, or just runs locally if you're debugging. And that serves up the web pages that the user interacts with. But it is a Flask application rather than Zope, so it's a relatively simple framework, which
That decision was made by others before us, by the way, the Flask decision.
well, yeah, but I mean, we would have changed it if it didn't make sense, and I think that it serves the needs, and I think we were a little bit dubious about whether it would be extensible enough for some of the things that we want to do with it, but we haven't actually run into problems using Flask, I don't think. In terms of database, things go into PostgreSQL instead of ZODB. They're both good databases.
Although interestingly, we've been using more and more of the JSON stuff in Postgres because not being tied to a schema at development time is really helpful, especially for games like Grid Universe, where you want to support lots of different options. And
it's hard to predict all the different things that one particular experiment might want to record, different events that might happen, different questions that might get asked in the questionnaire. So it's easiest just to have, a questionnaire answers column that is JSON, as opposed to provide a way for the experiment to configure its own schema for the database.
Yeah, in the past, it was originally the schema had quite a few sort of arbitrary property fields that experiments could use in whatever way they felt like, property 1, property 2, property 3, because you don't really want every experiment to extend the schema of the database, because then it becomes difficult to run multiple experiments off of similar databases and do analysis in a way that will work across experiments. Recently, we've moved that sort of property mechanism into JSON B columns and other things into JSON B columns, which allows experiments to have sort of arbitrary custom data that's indexable and searchable, and it seems to be working really well. And that's what allows things like that full replay of an experiment like Grid Universe, where there's a lot of stuff happening in terms of movement and actions that's recorded and can be replayed.
One big difference is the fact that this is a real-time system. It's not just HTTP requests going back and forth. We're using WebSockets. So you saw the demo. Whenever Alec is moving or sending a chat message or changing color, that is a message that gets sent to the server over a WebSocket that gets relayed to all the other clients, as soon as possible, so that they can display what's happening to other users. So in terms of the tech stack, that means we need to be running a server that handles WebSockets and handles asynchronous communication. So we're actually doing that using Gunicorn, which is a WSGI server that also has sort of a you can configure it with using gevent, and then it will handle things using an event loop.
Does anybody have any special questions about the tech stack? You saw this alphabet soup. Any questions about any of those things?
One thing in terms of deployments, currently it's tied to Heroku, but the plan is long-term to allow deploying to different architectures, to sort of university internal architectures. A lot of these universities have their own cloud stacks or shared clouds across universities. There are a bunch of different kind of recruitment mechanisms that social scientists use. Mechanical Turk is a big one, but there are things like Cloudflower and some Cloudflower.
Is Plan Out the Facebook's one?
What is that one?
Plan Out.
Plan Out. It's
is
something
a
that
Facebook.
Jordan's integrated.
I think it's a Facebook
API for.
It's for crowdsourcing something. I don't know what.
It's
on the horizon. We haven't used it yet.
Yeah, the project lead is integrating this Facebook API for something, and we're not sure exactly what it is, but it seems interesting. But in general, we're slowly making different aspects of the system pluggable, from the recruitment process, which we have a few options, but we want to add some more services to eventually deployment options. And in the end, the idea is that everything about the system can be configured in a simple sort of text INI file, and then you use this command. The experimenter uses a command line to launch. There'll be a number of canned experiments. There are already a number of experiments that scientists have written separately, demos that come with the project, separate non-demos like the grid universe that are sort of practical open source experiments that anybody can use and run. We're looking into basing some of creating ways to integrate existing JavaScript experimenting platforms into the experiment building framework, which is currently, Flask based, and we have our own kind of set of JavaScript tools for that. But there are some interesting frameworks out there for doing experiments using JavaScript that we're going to be integrating over time. So there's a lot more to do here in this future phases.
Yeah, for sure.
It's
We're not going to run out.
It's an interesting kind of space to be in, because a lot of these university departments have taken open source kind of to heart, but they're not programmers, they're social scientists, and they write the kind of code that scientists write. So although there's lots of things out there that people are used to and do specific things that we might need to do, they don't fit in with a high quality piece of open source software. So we have the difficulty of kind of moving people slowly from something they're used to into something that's reliable.
I have two questions on the tech stack. So,
yeah.
so one is, you talked about pluggability, and so one question is, don't you miss the CCA, and how do you work without that? And the other question is, I heard a lot about dynamic schemas and using JSON formats for that. So how do you handle evolving schemas as experiments evolve, and how do you do cross-experiment analysis then? If you have several flavors of the same experiment.
I'll take the first question. I haven't really missed the CCA, but the scope of a particular experiment, of writing a particular experiment, is basically writing some code that runs in your browser and writing some back-end views. It's not necessarily needing to change how the system as a whole works the way that we often do with Plone. So that's probably why I haven't. There are some pieces that are inspired a little bit from that. I mean, there's the idea of a recruiter. So you can have a Mechanical Turk recruiter, or you can have the hot air recruiter that just prints out the fact, oh hey, I'm recruiting somebody, but doesn't actually do anything. So like that is basically like a utility that you can configure which one to do. So I mean, there's some level of dependency injection happening, but.
And we are using the set of tools, entry point support, so we can reference classes in packages and get them by name and by type, which is kind of like a named utility lookup, but it's sort of a first-class Python thing that people are a bit more familiar with and has less boilerplate to set up. So it's a couple of extra lines in your setup PY. And as David says, generally speaking, these are spun up once on a Heroku server. You don't have to deal with having a big install with 20 different things and configuring which ones you want in a particular experiment run.
Right. I suspect if we ever get to the point where we want to allow third-party packages to add their own recruiters or their own infrastructure deployment mechanisms or things like that, that we may need to look into
having some sort of registry.
Yeah, having some global registry, and it might just end up being the setup tools entry points like we use for experiment registration. But that's something we haven't needed to think about yet. Right now, it's all, those aspects are all encapsulated within the package. But maybe at some point we'll need to allow having external packages add recruiters or deployment mechanisms.
Can one of you speak to his other question about repeating experiments if the schema is evolving?
Well, I mean, so do you mean in terms of like, because we've changed the database schema away from this sort of property-based thing to more JSON-B, that means because it was early on in the process, you know, we don't expect people to be comparing experiments run across those two versions of the database. They're sort of on their own with that. But now that
That's the get rid of backward compatibility part.
right, but now that we've moved to using JSON be like a sort of generic column for question responses, a sort of generic column for information from an event in the experiment, it becomes a lot easier to compare those things. If somebody makes a change to their own JSON representation of experiment data, then it's on them to figure out how to compare those things across different runs, but they probably shouldn't be doing that if they want to compare it.
Also, scientists are a lot more cautious when it comes to what exactly was the version of the software. So when we upload to the Open Science Framework, we upload a zip of the actual deployment that ran on Heroku. And I think a lot of scientists would be nervous about the idea of opening up a data set created with one version of the experiment with a different one that potentially has subtle differences in exactly how things work. So I suspect if we ever did have to compare people in two different versions, we would have to have something like the analyze function we have in GridUniverse that pulls out the data for that specific version. And then we would say, well, this was one with version 1 and this was one with version 1.4. So we have to use the version 1 and the 1.4 analysis tools and then compare the analyzed data.
Right. Yeah, like you said, if these experiments, once they're run and uploaded to the Open Science Framework or similar, if somebody else wants to run them, they'd pull that down and they would get the exact same set of code.
And that includes a requirements file that says, you know, install this version of the software.
Right. So in theory, you wouldn't, if you were running the same experiment, you wouldn't have a schema change ever. If you do have a schema change, then you're effectively running a different experiment.
And we might have problems with that in future when APIs change and get deprecated, but that's a problem for the future.
Yeah, really. So we have about 10 minutes left, so I'm going to suggest that we kind of breeze through the next couple sessions, so we have time for the fun technical challenges.
Sure. I mean, just to say some of the things that we've done, like we're trying to support people who aren't, you know, full-time developers in getting started with building an experiment. We've drawn inspiration from the tools that are provided for full-time developers, you know, especially in a lot of JavaScript frameworks these days. You get the tool, you run a command to generate a skeleton. We've had something like that in Plone for years. So we have a cookie cutter template to create a starter experiment. We have some base templates that are, you know, like the first page of the experiment, the consent page, the instructions, the actual experiment, the questionnaire are all pages that you can either, you know, inherit the default or override it to fill in your parts. And then there's a JavaScript library that takes care of a lot of the communication between the front end and back end, so you can just make a call to that as opposed to needing to think about what the API endpoints are.
And then just a little bit about what about the Dallinger users, that is the experimenters writing experiments. Documentation is obviously important. It started out sketchy, it's getting better. It needs to get better still, I think. There's a Slack channel that we have. There's a general channel where we work doing the development kind of discussions, and there's a help channel where new users can come ask questions, and all of the Jazkarta and combined teams from Arizona State and Berkeley and everybody pitch in to help users in that channel. Anybody want to say something about
Oh, just, I mean,
local debugging?
Local debugging is obviously important so that you don't have to go to the overhead and time of actually running something on Mechanical Turk and Heroku every time.
But
Right.
Also, we have this pain with Plone of you have to restart the server, and every few years people come up with things like Plone Reload, and there was Roadrunner for a while for doing tests and things to shorten that loop. And we have exactly the same problem with Dallinger because we have to package up an experiment and then run it locally. So we've been looking at lots of tools.
Trying to make sure that as you're making changes, you can see them immediately without needing to restart the experiment necessarily.
Yeah.
So let's move on to the question of code quality. So
we've learned a lot from our experience in the Plone community, obviously, about testing and QA and that sort of thing. So we don't have 100% test coverage, but we're progressing in that direction, and we have automated tests that run on Travis and will break if we decrease our code coverage. And we also try to be diligent about code review, making sure that things go through a pull request process and get looked at by somebody else before getting merged.
Okay, fun technical challenges. Let's talk about some of them. So yeah, we have a short list here. We can talk about that, and if anybody wants to talk about something else, wave your arms and we'll take, okay, so maybe we should take some questions before we dive off here. Yeah, because we just have a few minutes left. There were some questions.
I just have one small question, which is only partly technical, but that is about participant selection. So if you want to do a large social science experiment, how do you ensure that you recruit the participants in such a way that they are a representative sample of the population you wish to examine? And if you start by, for instance, if you recruit through the Mechanical Turk, then your sample will already be skewed because you are recruiting amongst Mechanical Turk users. So how do you compensate for that, or do you need to compensate for that?
It's basically a question for the social sciences. You know, if you know something about Mechanical Turk, you know there are some criteria that you can choose, but of course that's a skewed sample of humanities. So yeah, I don't know. That's a question for each experimenter and each experiment, how they handle those kind of issues, for sure.
This is where repeatability is really something nice that we have, because we have this pluggable recruitment system. You can use a recruiter that gives you a URL and you give it to people in a laboratory. So you could run an experiment on Mechanical Turk with 1,000 people, draw some conclusions, and then rerun smaller scale things in a lab or with other sources of participants to verify that your conclusions were accurate despite the fact it was a skewed sample of people.
And also, I mean, it's worth comparing this to the status quo, which is that they typically only do that sort of local, very small study. So this is at least something that you can compare to.
Yeah, right. Generally, social science experiments are run with university graduate students. So there's a lot more possibilities at least.
Right.
Here.
The Mechanical Turk sample is generally broader than like the, set of students who are willing to participate in a social experiment on a university campus.
Right.
But there are filters that you can use when you're running a Mechanical Turk experiment that can be set up in the configuration.
Such as by region or what browser support you have. Things like that.
Yeah, I think age they can filter on too. I mean, I think there are some demographic things they're not allowed to filter on and demographic things that they are allowed to filter on. And then, like I mentioned, there are other tools that are more specifically oriented towards recruiting for social science, like Crowdflower, and there's like 2 other ones besides Mechanical Turk that allow much more refined ways to limit or define your sample. And eventually we're going to be trying to integrate with those services.
So that's the importance of having pluggable recruiters to be able to address those kinds of questions.
Right.
Yeah. I think you had a question also?
Kind of on his line, the filtering issue is how much control do the scientists have? And is that part of the development as this continues? But all my other questions would have to go to Berkeley.
Yeah, right. Yeah.
I actually worked with Dr. James Greer Miller, who created the very first behavioral science department at Michigan State.
Cool.
And we did a lot of work together.
Tom Griffiths is the name of the PI on this.
Okay.
At the Cognitive Science Lab.
Yeah, because I'm more interested in his falsification procedures and
we could put you in touch with the source of all that kind of thing. But for sure, the answer to your sort of
because there are different
question,
cognitive functions operating in the method that you're using against what they're planning or testing as the tentative hypothesis. So that's a whole other world, though.
Yeah, that's the social sciences world. Our world is to make sure you've got a good pluggable system for recruiting, and so that people can control how they do that.
Right. Yeah. Time's up.
All right.
That was a real fascinating talk as far as I'm concerned. So thank you very much.
Thanks.
Yeah.
Thanks everybody for coming.
Thank you.